on, what day is it today? Tuesday? And then in 2 days is Thursday? That's how it goes? Wednesday, Thursday?
Most weeks.
Okay. So on Thursday, I'm going to give you a problem set. Okay, something that's due. If you haven't done at least some of the practice problems yet, I would strongly recommend that you get to that before the problem set, because the idea with those practice problems is that you sort of drill the fundamentals, get some stuff in your head, and then when the harder stuff rolls out, you have something to kind of fall back on. Yeah, I'll do that as soon as I can, yeah. So far we've been talking about statics of particles, and there's not too much more to say about that. You just add up all the forces, set them to 0, all the forces on the particle. So now we're going to talk about rigid bodies, and now things start to get a little more complicated. Not too much, though. I bet that was someone in this class who's just like, ugh, I can't go in there again. Maybe Thursday. Just doesn't feel right today. Okay, so with rigid bodies, you have objects that you're treating as having some measurable size, some non-zero size. That was the thing with particles, right? We're assuming everything just happens at the center of mass of the object. Now we're assuming that you have some length. And having that length means that the location where you apply forces starts to matter. Locations of forces matter. And as an example, so say you have this car. This is a bird's eye view of a car. There's its windshield, back window. If you apply a 50,000 Newton force here, you can imagine what happens. That car just goes accelerating off straight up the page. If you apply that 50,000 Newton force here, something different happens. You still get that same acceleration of the center of this car. But in addition to that, you make this car spin around, right? And so that's what we're going to talk about. That spinning comes from moments of forces about a point. And that's the first thing we're going to talk about. So moment of a force about a point. And you guys have talked about this before in 1121, but you probably did it more in terms of thinking of like perpendicular distances, right, and then vector components. So we're going to do it all in terms of vector components now. And in a way, it makes everything simpler because once you sort of get the technique down, you get into a rhythm of doing it, there's not really any thinking involved, when you're trying to figure out perpendicular distances and everything, you have to think like, okay, is that a cosine or a sine? And what do I? You kind of are not going to have to do this anymore, but the math is a little bit more involved. It's not too bad. And normally when you talk about this topic, you think of, and people say just sort of engineer slang for this is moment, right? You talk about a moment or a torque. But I want you to really beat into your head, not literally, but figuratively beat into your head that whenever you hear the word moment or torque, you're talking about the moment of a force about a point, okay? Those two things are just as important as the fact that it's a moment, okay? Without defining the force and without defining the point, it doesn't mean anything, okay? It's like talking about cosine without talking about an angle or something. You don't have anything until you define those two things. And what do these moments of a force about a point do? They cause angular accelerations. I don't know how long I'm going to use this acronym. It seems a little ridiculous, but just to emphasize, at least for today, the importance of the force and the point, instead of talking about moments, I'm going to talk about moments of forces about points, and I'm going to write it like this: moment of force about point. Okay. So the definition of the moment of a force about a point, a MOFAP, is the moment about A produced by the force F, and this is a vector quantity, is equal to rho, and I have to tell you what that is, crossed with the force vector. And this is our equation 2. This class is great because you only have we're only going to have 5 equations in the whole class. And it's just going to be using them over and over and over again. So this is equation 2. So with that few equations, you know that the ones I put numbers on are going to come up a lot. It's important. Where this vector rho is the vector going to the location of force application, where that force is applied, from the about point. Okay, so in this example, say that our about point, say we chose the center of the car as the about point, okay? Then this point right here is the location where the force is applied, right? That we don't get to choose. That's chosen by the problem itself. And so we're going to take a vector that goes from the about point to the point where the force is applied. If I call this A and this P, someone tell me how you calculate that vector rho. It's P minus A. Oh, P minus A. Right idea, but P minus A gives you that vector rho. And in order to calculate these, I'm going to always write this in terms of a table that just makes it really easy, the bookkeeping. So think of these moments of a force about a point as being represented by this table. And you just fill out the columns of this table. So the first column is the point where the force is applied, the point of force application. I'll call that P, just like I did in this figure. The second column is the about point. That's the one you get to choose, and I'll call that A. The third one is rho, and rho is then just equal to P minus A. The fourth one is the force vector. And then the fifth one is the moment of the force F about A, and it's just equal to the cross product of rho and F. Okay. So if you get in the habit of just filling out this table, doing this calculation is sort of trivial. And we're going to see that when we go to the rotational version of Newton's second law, right, when we use Newton's second law, we add up all the forces on the body. When we use the rotational version of Newton's second law, we're going to add up all the moments on the body about A. So we can just fill out this table, fill out the first row, that's the moment produced by the first force. Second row is the moment produced by the second force. And in the end, you have this column of moments that you're going to just add up and put on the left side of the rotational version of Newton's second law.
So
yep.
P and A are points, so they're zero vectors is what you're saying?
No, they are locations. So wherever you put your you're right, they're points. So wherever you put, say you put your coordinate system here.
Okay.
Like that, okay?
Yeah.
Then P is going to be, say, 3, 3.
Yeah, okay.
A is going to be 5, 0.
Okay.
Okay? Okay, so let's do an example and fill out this table. And I guess this example sort of mirrors this car that I drew on the right. So let's say that we have this 50,000 Newton force acting in the lower right corner. And let's say that the length of this object is 2 meters. Go another 2 meters. And one meter up, and you get what we'll call the about point. Okay, and we're going to calculate the moment of this force about this point A. Our P, we don't get to choose. That's just where that force is applied. Starting to get a little cluttered. All right, so let's write the table and start to fill it out. So we have where the force is applied, the about point, rho, which is just P minus A. Then we have the force vector, and then we have the moment about A produced by F, and that's rho cross F. Okay, so before we can fill out any vectors, we need to choose a coordinate system. We're going to do a lot of 2D problems, and most often you're probably just going to choose a standard horizontal, vertical coordinate system, but you don't have to. The coordinate system can be rotated anywhere you want. And so I'm just going to kind of point out over and over again that, like, we can't start writing vectors yet. We got to choose something to reference those vectors to. So let's choose our coordinate system right at the middle of this object, like that. Okay. And this point A is supposed to represent the height of this. You know, that's 1 meter to the, like, that point A is right at the horizontal with the top edge of that object. So this object is 1 meter high, 2 meters wide. Okay, so what are the coordinates of that point A? That point P?
1, -half.
Right. So 1, -0.5. And then to do the cross product, I'm going to write all these as 3-dimensional vectors. Okay? So doing this for a 3D problem isn't any different. You just have to figure out all the components instead of just figuring out 2 components. And what are the coordinates of the point A?
3 positive half.
So 3, and then a full 1, because it's all the way up at the top of that.
Well, you're starting in the middle.
Oh, starting in the middle, thank you. And then for rho, just subtract those. So -2, -1, 0. And what's that force vector? It's y. So 0, 50,000, 0. And now to compute that cross product, if you have 2-dimensional, if you're doing a cross product of 2-dimensional vectors, the cross product is just this x times this y minus this y times this x. So you got, and that's in the z direction. So you got 0, 0. It's always, when you take the cross product of two-dimensional vectors, you always end up with a value that's only has a z component. So 0, 0, and then -100,000. And of course, just to keep beating this horse, this dead horse, you'd get a totally different answer if we'd chosen a different about point, right? If we'd chosen our about point at P, go ahead and calculate that in your heads. What would the moment be if our about point was P? 0, right? Okay, so what would happen now? I want to sort of emphasize the vector nature of these moments. Like, these moments are a little like a force vector, maybe just because you're so used to dealing with force vectors, it's kind of easy to imagine a force vector as being an arrow in space, right? And if you change the coordinate system, rotate the coordinate system, it changes the components of a force vector so that it still represents that same arrow in space, right? Like, if this is your force vector, right? Let's do this. So and your coordinate system is horizontal and vertical. Then you have a 0x component, positive y component, 0z component, right? Now take these coordinates and rotate them like this. It's still going to represent this same arrow, but now it's going to do it by saying 0x component, negative y component, 0, right? And so let's do the same calculation with the moment and just see that it's the same thing. It's a vector quantity just the same way as a force is. It's an arrow that just lives in space. To get numbers out of it, you define a coordinate system, but it lives in the same spot in space no matter what your coordinate system is, okay? So now, question, what if we had the same problem, but we switched the coordinate system to be at the top left corner and rotated this way, okay? So now our problem looks like this. We have our coordinate system here. We still have our force here of 50,000, and we're still calculating this moment about the same point A, okay? Well, what do you expect? What do you expect to see? Can anyone do this in their head? Look at the answer we had before, I guess, first. So our answer before was in the z direction, so out of the page, with a value of negative 100,000, right? So now we've rotated the x and y axes. The z-axis, where's the z-axis pointing? It's still pointing out. It was before, right? And since that z-axis is still pointing out, we should get the exact same vector, right? It would change the x and y components, but since all we had was a z component for that moment vector, we should get the same vector with this calculation, okay? So let's just do it again. Fill out the table. So we have the point where it's applied, the about point, the row vector, force vector, and the moment about A produced by F, and that's equal to rho cross F. Okay, so what's the point P in this new coordinate system?
-2, 1.
Yeah. And what's A?
-3.
4, yeah. And 0, right? So rho then is -2 minus 4, so +2. 1, 0. What's the force vector in this new coordinate system?
0, -50,000.
Right. And so the moment is 2 times -50,000 minus 0. That's in the z component. So same vector again. Okay. And um, the way you're used to thinking about the moment, probably more used to thinking about the moment, as a force times a perpendicular distance, right? When you um, when you calculate a moment that way, you don't have to come up with a coordinate system in the first place, right? So something would be really screwy if changing a coordinate system gave you a different vector for the moment, right? Um, like you're used to the fact that a moment is independent of the coordinate system you choose, and this shows that it is. Although, if I'd rotated that coordinate system z-axis, we'd get different numbers. It would just represent the same vector, right? Am I talking about this too much or too little, or just right? Just right. Thank you. That's what I thought. Okay, so let's do a little more involved example. But we're still going to use these exact same steps. So say that you have this plate that's hinged to the wall over here. We'll put our coordinate system right at the top. Okay. You see what I'm getting at with this? These are in line with these are supposed to be in line with all the sides and edges. And this plate is 2 meters long. Oh, and let's go X, Y, Z. So that's just the coordinate system. 2 meters long and 2 meters long this way. And 1 meter above the top face of this plate, a cable is connected from the center of the plate. Okay, so that's supporting this thing. And if you think about this, just think physically about this. Would this stay up? Yeah, as long as that cable holds and stuff. The hinge and the cable together will hold this in place, right? And let's calculate. I'll give you about point A. Let's calculate the moment about A produced by that cable, okay, by that cable tension. And this is the moment about A acting on the plate. So I'm not talking about like the moment on the wall or something. So what's the moment about A produced by the cable force? And we don't know what the tension in that cable is, but for now, we're going to assume that that cable tension is just has a value of T, okay? So we're just going to use a variable to represent it. I'm going to do this the same way. The one thing that's different about this is that we don't have numbers for the force vector, right? All we have is, I mean, we're going to come up with a force vector, but it's going to depend on this variable T. So as a first step, we know we're going to have to represent that force vector. So let's figure out what that force vector is in terms of the single variable t. Okay? We can figure out the direction, come up with a unit vector, multiply it by t, and that'll be our force vector. Okay? So the force applied by the cable. So first, how do I get that unit vector? What are the steps for getting the unit vector in the direction of that cable force? We know it's going to be, we're talking about the force on the plate, so it's going to be pulling this way. You can't see that. It's going to be pulling this way, right, towards the wall. We know the coordinates of this point. I guess I didn't write that, but that's supposed to be 1 meter. Yeah. Okay, so this point here is going to be, what's that in coordinates? -1, +1, and then +1. So -1, 1, 1. And then minus the other end of this cable, which is, that's where we put our origin. So that's just zeros. -1, 1, 1. Okay, so that's a vector in the right direction. Okay, but it's not a unit vector yet. So we need to scale it. So
May I have your attention, please? This is security. This message is to inform the campus community that ITS is still working to restore technology services to the campus. These services are expected to be restored by approximately 11 o'clock a.m. We apologize for the delay and thank you for your patience.
that was helpful. Okay, so what's the length of this vector? Square root of 3, right? So the unit vector is going to be 1 over -1 over the square root of 3. I can't fit it in there. -1 over square root of 3, 1 over square root of 3, 1 over square root of 3, and that's -0.577, +0.577, +0.577. Okay? And so now all we have to do is multiply that by the variable. So the force applied by the cable is just T times -0.577, 0.577, 0.577. And now we can set up that table. So P vector, A vector, rho vector, just subtract those two. Force vector, and then moment about A produced by F. All right, so where is the force applied to the plate? Right. And what are the coordinates of the about point? Yep. And so rho is just 0 minus -1, 0, 0 minus +1. The force vector we just calculated. And so now we just need to cross rho and F to get the moment. So let's see, you have to go back to the formula for the cross product, but so in the X component of the moment, we have rho Y times Fz, so that's 0, minus rho Z times Fy, so 0.577 T. The Y component, we have 1 times 0.577 T minus 1 times 0.577 T, and then the negative of all that, but that just comes out to 0. And then finally in the Z component, we have 1 times 0.577 T minus 0, so 0.577 T. Any questions about that? Or any of the steps to doing that confused you? Okay, so up until now, talking about moments, moments of a force about a point are just sort of this mathematical thing, right? We haven't used it for physics in any way yet. So in order to use this for physics, we need some kind of law of physics, and we're going to use the rotational version of Newton's second law. So rotational Newton's second law lets us connect it to physics or dynamics or whatever you want to call it. And the rotational version of Newton's second law says this. It's actually sort of complicated. That's not what it says. Okay, and this is true for rigid bodies. The sum of the moments on the body about A is equal to the moment of inertia about A times the angular acceleration. And the sum of the moments about A, that's a vector, right? The angular acceleration is also a vector. I'm talking generally if we're doing three-dimensional problems. What type of mathematical object is this moment of inertia? You guys talked about moments of inertia a little bit, right, in physics. So when you use it with two-dimensional problems, like probably maybe all of the problems you've done, you can treat that as just a scalar. But in general, in 3 dimensions, that's actually a 3x3 matrix. And we're not done yet. If you think of the analog, Newton's second law, you just write this stuff down. It's simple and compact, and that's all there is to it. But now this is a little more complicated because this is only true if we have the same about point for the moment as we have for our moment of inertia. That's an extra level of complexity. And then even more complexity comes from these conditions that we have to put on this for the rotational version. This equation only holds when A is a point on the body that's either, anyone remember what these two things are? What are your two choices if you're going to use this simplified version of the rotational Newton's second law? That's going back into the vault. If either that point on the body is fixed in your coordinate system, so you're at like a hinge of some kind, okay? So fixed in some inertial reference frame, or it's the center of mass of the body, okay? And if you want to deal with doing this calculation for any other points, things get really complicated. You can't use this idea of moment of inertia. You have to write out this multi-term thing. I guess maybe the reason that I am giving you all this information is because a lot of you are probably going to take dynamics with me, so that's a head start on dynamics. But also, it's like to get you to be thankful for what we have in statics, because things are way simpler in statics. Okay, this is dynamics, right? Just like when I talked about Newton's second law for particles, I gave you F equals ma, and then for our case we reduce it to F equals 0. Okay. In statics, the rotational version of Newton's second law is just the sum of the moments about A is equal to 0. And I'm calling that equation 3. And that's all there is. So look how much simpler that is to use. This about point can be anything, okay? It doesn't even have to be on the body, actually. We can just pretend like it's attached to the body. We can pretend like there's a wire connecting the body to this point out in space, okay? So choose any about point you want. Calculate all the moments about Paul. Hey. You're missing the good stuff. Choose any about point you want, add up all the moments, and set them equal to 0, and that's all you need to use this equation. So let me summarize what we have for a rigid body. For a rigid body, in static equilibrium, we have two equations. The sum of the forces acting on that rigid body are equal to 0, and the sum of the moments about any point you want are equal to 0. And those are true in 2 dimensions or 3 dimensions. If we have a 2-dimensional problem, how many useful equations do we get out of this set of equations? 2-dimensional problem, like what you're used to, you know. 2 from the force equation, because it's 2 dimensions, right? You do have that third equation for z, but it won't help you because it just says 0 equals 0. And then one more equation for from the moments, okay? The z component of that moment equation. and then 2, 0 equals 0 that don't help you. How about in 3D? How many equations do you have, useful equations? 3 for the force equation. How many for the moment equation? 3 more. Yep. So in 2D, that gives 3 useful equations. In 3D, 6 useful equations. And so that tells you how many variables you can solve for using these, right? If you're doing a 2D problem, you can deal with 3 variables. If you're doing a 3D problem, you can deal with 6 variables. The bad news is you usually, the type of reactions that you're looking for just increase in dimension when you go from 2D to 3D. So you think you have all this extra computing power, but really you're sort of just treading water. You know, like for example, if you have a, let's say you have well, the easiest one is a fixed joint. So say you have like a cantilevered plate coming out of a wall, okay? And you apply some force to it and you want to figure out the reactions between this cantilevered plate and the wall, okay? If you're doing it as a 2D problem where you're just looking at it from the side, then that wall produces 3 unknown reaction loads, a 2-dimensional force vector, and a single component of a moment due to a couple. We'll talk about couples. So 3 unknowns. So now how about if you do it as a 3-dimensional problem? Then you get all these extra equations. But the bad news is, looking at it in 3D, that wall provides a 3-dimensional unknown force vector. So that's already 3 unknowns. And it also provides a 3-dimensional unknown moment. So there's your 6 unknowns, and you have 6 equations, but you're no better off, you know. Who knows what I'm talking about? Good. Everyone else talk to them. And we'll use these to calculate, like in this class, pretty much always. We'll just use to calculate reaction loads. There was something else I really wanted to say, but now I'm embarrassed. Not really. I can't remember what it was. And I'm embarrassed about that. Okay, that'll come to me later. Anyone have any questions about where we are so far? So we have these 3 equations that we can do statics with in 2 dimensions, 6 equations we can do statics with in 3 dimensions. So now I want to talk about a very specific and important type of, like we've been talking about moments of a force about a point. I want to talk about a very specific kind of moment that's going to come up all the time. And it's pretty interesting how this works. And this is the moment of a couple. Do you remember talking about couples at all in 1121, 1128? Yeah, 1121, I guess it would be. That word didn't come up as you remember. In D form, we talked about couples, right? And what do you notice just about the phrasing here? Moment of a couple. We've been talking about moment of a force about a point. So when I say this, there's no about point in the name, right? And the answer is, and the reason these are so important, is moments produced by a couple, and a couple is just two equal and opposite forces. So I mean, it's really like the moment of a couple is just the combination of a moment produced by this force and the moment produced by that force about whatever point you choose, right? But we're going to see that when you calculate the total moment produced by a couple, the about point doesn't come into it at all. It's a really surprising, interesting result. The about point isn't going to matter. And what that is going to mean is when we use the rotational version of Newton's second law, you're going to, like, you have to choose an about point to use this, right? So say you choose this point, and now say there are some couples in addition to just lone forces that are producing moments, okay? Then you're just going to be able to add these couples into the left side of this equation without adjusting anything for an about point, because they're exactly the same for this about point as they are for this about point or this one, okay? So couples are just something you can always add into that equation without worrying about the about point. Okay, that's just kind of a heads up on where we're going. So let me define a couple. A couple is made up of two equal and opposite forces acting at some distance apart. I don't know. We could debate that all day. Yeah, right. Acting at some distance from each other. So there's some object, and you have some force F, and you have another force F just acting in the other direction, same magnitude. Okay. So they have to be parallel like that. They have to be the same magnitude, and that defines a couple. And it seems a little weird when you think about, so what is the moment of a couple? It's just the moment produced by this force about some about point A, plus the moment produced by this force about some point A. There's really nothing, to me at least, that immediately tells you that that about point isn't going to matter. But I'm going to show you in sort of an abbreviated notation. I think it'll at least make sense to you how this works. And if you wanted to prove this in using the notation that we've been using up to now, you could. It would just take a while, because you just have to write a lot of stuff out. So I'm going to show that in calculating the moment produced by a couple, the about point doesn't matter. Okay, so let's, I'm just going to draw out what our example, like what our test case is. So you have some random rigid object, and you have some force vector acting here. I'll call it F. And you also have some force vector acting here. It has to be equal and opposite, so that's just going to be negative F, right? Each component is going to be negative. And let's take some about point. The about point has to be fixed in this body, but that doesn't mean it physically has to be on the body, right? So in general, it could be anywhere. It just has to, you just have to imagine that this, as the rigid body moves, this about point moves with it. So if this is our point A, then let's call a vector going from A to the point where the force F is applied, rho 1. And from our about point to where this force of negative F is applied, we'll call that rho 2. And if this point here is P1 and this point here is P2, okay, then like we've been doing with the tables, rho 1 is equal to P1 minus A, rho 2 is equal to P2 minus A. Okay, this is just like a pop quiz. So what am I trying to show here? What am I trying to prove? Because I know, like with proofs, I remember like I'd sort of get bogged down in the details. Really, the big picture is the key here. What am I aiming towards?
A is gonna fall away.
That's right. That the A is going to fall away when I calculate this total moment about A. And now, so I'm going to just calculate the sum of the moments about A. So the moment produced by the force F is rho 1 cross F, which is P1 minus A, crossed with F. And now just add the moment about A produced by the second force, this force negative F. So plus P2 minus A crossed with negative F. And now I'm going to do some stuff. I don't think you guys probably have taken math classes where you've done a lot of manipulating cross products and stuff. But so I'm going to use some properties of cross product that you can easily believe, and you could actually verify to yourself if you wanted to. But the cross product is distributive. Okay, so this is equal to P1 cross F minus A cross F plus P2 cross negative F minus A cross negative F. So that happens because the cross product is distributive. And now you can pull these negative signs through. Those are just negative constants multiplied by these cross products. So you get P1 cross F minus A cross F minus P2 cross F, okay? And you can see that's sort of the step where you see how things are going to happen, plus A cross F. And negative A cross F and positive A cross F go away, and now we don't have any A's left. And we're left with P1. I'm using the distributive property again to recombine these. P1 minus P2 crossed with F is the total moment about that point A produced by that couple. And since there's no A in there, that's the value you'd get no matter what about point you chose. Okay. So that's what you'd get for any about point. So that gives equation 4. For any couple where the force vector F acts at P1 and the force vector negative F acts at P2, the moment produced by that couple is equal to P1 minus P2 crossed with F. And that's equation 4. And just like, by the way, as a heads up, what we're going to see is that any rotational restrictions provided by a reaction, like that cantilever plate that I was talking about before, its rotation is restricted, right? The wall doesn't let it rotate, okay? That restriction is provided by a couple. The wall applies a couple to the plate, and actually, if you think about it, it sort of makes sense that it's a couple because what the wall's doing is applying, like if you're applying a force to this thing here, what kind of loads is the wall applying to this in order to keep it from rotating? It's applying a force this way and a force this way, right? I mean, say that's glue. Like, it's not really applying a pure moment in a way, even though that's what we're going to treat it as. All glue can do is apply forces, but it applies these forces in pairs that look like this. Okay, and so that's why we can treat that as a couple, because it's made up of infinitely many actual couples. So now I'm going to do an example with real numbers. I mean, not as opposed to complex numbers, actual numbers. So say that you have this object, and here you have a force of 50, negative 10. And here you have a force of negative 50, 10. This point is 0, negative 2. And this point is 3, 0. Okay. And we want to know what's the moment produced by this couple. And that brings up sort of a, like, it's all well and good when you're talking about variable names, right? Like, so we have this nicely named positive variable f, and this nicely named negative variable negative f. But what happens in a case like this? Like, this is a couple. They're equal and opposite forces. But which one do we call negative f and which one do we call positive f? Doesn't matter. That's exactly the thing. What matters is that whichever one you call positive f in using that formula, you associate that point is what you call P1 in the formula. Okay? So it's arbitrary, but let's call our positive force 50, negative 10. Okay? Then once we make that decision, we're locked into defining P1 as 0, negative 2. And that means, our negative f is negative 50, 10. And our P2 then is 3, 0. So the moment produced by this couple is P1 minus P2, 0, negative 2, minus 3, 0, crossed with 50, negative 10. So that's negative 3, negative 2, crossed with 50, negative 10. And that is 0, 0, and then 30 plus 100. Okay. And does this make sense? Think physically about what's happening here. If you have basically, these are mostly horizontal forces, right? So this force is mainly going this way. This force is mainly going this way. So think about the rotation that combination will cause. It'll cause a counterclockwise rotation about the z-axis. Counterclockwise is positive, so that makes sense. Okay. Any questions about that? Okay, well, I think that's good for today. But please get to those practice problems as soon as you can. And Thursday, I'll get a problem set to you and some more practice problems. So I would strongly recommend just don't let stuff start to pile up. If you just keep doing a little each day would be ideal. This stuff will keep making sense, I think. Yep.
So is the practice problems due like Tuesday next week?
The
Or
the problem set.
Yeah.
I think I'll give you a week usually, always probably.
Okay.
So it'll be
A
next
week,
Thursday.
okay.
And you're gonna post the answers to the practice.
Yeah, I'll get those up as soon as I can. Yeah.
Have you posted anything since